Welcome, everyone. I'm excited to kick off our presentation today. The topic is heat transfer and temperature measurement. We'll explore how heat moves between objects and how we accurately measure temperature. Over the next few slides, we'll cover the fundamental principles, techniques, and applications. Let's get started. Let's take a quick look at what we'll cover today. On this slide, we see the contents of our presentation. We'll start with the concepts of hot and cold and how we measure temperature, including the use of laboratory thermometers. Understanding how to read a clinical thermometer is also important, especially in medical settings. We'll explore the different ways heat transfers, through conduction, convection, and radiation, and see how these processes work in everyday life. For example, convection in air explains phenomena like wind or how hot air rises. We'll also look at how heat is absorbed and transferred in different materials, which is crucial for understanding climate and weather patterns. Moving on, we'll examine convection again, but specifically in the context of air, like the sea breeze and land breeze, which are wonderful examples of how temperature differences drive movement of air. Finally, we'll discuss how our clothing choices change with the seasons, which ties back to how we manage heat and stay comfortable or warm. Throughout this presentation, the overarching theme is understanding how heat moves and affects our environment and daily lives. Let's talk about hot and cold objects in our daily life. We encounter many different objects every day, and some are hot while others are cold. For example, a steaming cup of tea is hot, while ice is cold. You might notice that some objects are hotter than others, and some are colder. Often, we decide which object is hotter or colder just by touching them. But it's important to remember that our sense of touch isn't always reliable for measuring temperature. That's where the concept of temperature comes in. Temperature tells us how hot or cold an object is, and we measure it using a device called a thermometer. Understanding temperature helps us compare objects more accurately than just feeling them. This idea of hot and cold, and how we measure it, is fundamental to understanding the properties of different objects and how they behave. Today, I'll be talking about clinical thermometers. These are essential tools in healthcare for accurately measuring body temperature. They play a crucial role in diagnosing and monitoring illnesses, especially infections that cause fever. Clinical thermometers come in various types, including mercury and digital models, each with its own advantages. The key point here is their precision. These devices help healthcare professionals get reliable readings quickly. Understanding how to properly use and interpret these thermometers is vital for effective patient care. As we move through this presentation, keep in mind that accurate temperature measurement is fundamental to assessing health status and guiding treatment decisions. Let's take a closer look at digital thermometers. These devices have become a crucial part of modern health monitoring because they offer quick and accurate temperature readings. Unlike traditional thermometers, digital ones display results instantly on a screen, which makes them very user-friendly. They are especially useful in clinical settings or at home when you need reliable data fast. One of the key advantages of digital thermometers is their precision. They can measure temperature within a fraction of a degree, which is important for accurate diagnosis and treatment. Plus, many models come with features like memory recall, so you can track changes over time, and some even have alerts if your temperature is unusually high or low. Connecting this to our overall theme, digital thermometers exemplify how technology is improving healthcare, making it more efficient, accessible, and precise. They are a perfect example of how innovation continues to enhance patient care and health management. Now, let's talk about how we measure body temperature using a clinical thermometer. This device is specially designed for that purpose and is called a clinical thermometer. It consists of a long, narrow glass tube with a bulb at one end, which contains mercury. The mercury expands when it gets warmer, allowing us to read the temperature. The thermometer has a scale marked in degrees Celsius or degrees C, which helps us determine the exact temperature. Typically, it measures from 35 degrees C to 42 degrees C, covering the range of normal and fever temperatures. One important feature is the small kink near the bulb, which prevents the mercury from falling back down after we take a reading. The normal body temperature is around 37 degrees C, which is considered healthy. Remember, this device is essential in medical settings for accurately checking if someone has a fever or if their body temperature is within the normal range. It's a simple but vital tool in understanding our health. Let's take a moment to talk about the concept of a kink. In this context, a kink refers to a bend or curve in a material, and it's a term often used in physics and engineering to describe how materials deform. Moving on, mercury is a key element here because it's commonly used in thermometers due to its unique properties. Its ability to expand uniformly when heated makes it ideal for precise temperature measurements. Now, speaking of thermometers, the clinical thermometer is an essential medical device that helps us measure body temperature accurately. It typically contains mercury for the reasons I just mentioned. Finally, the numbers 1, 2, and 3 might seem simple, but they often represent steps or stages in a process, such as the steps involved in measuring temperature or understanding material deformation. All these points connect to our overall theme of understanding how different materials and tools behave and are used in practical applications. Now, let's talk about how to properly read a clinical thermometer. First, it's important to wash the thermometer thoroughly with an antiseptic solution to ensure cleanliness and prevent infection. Once it's clean, hold the thermometer firmly in your hand and give it a few quick jerks. This is to bring the mercury level below 35 degrees Celsius, so we start from a known baseline. Next, place the bulb of the thermometer comfortably under your tongue, making sure it's in contact with the moist tissue. Stay still and wait for about 1 minute to allow the thermometer to register your body temperature. After that, carefully remove the thermometer and look at the mercury level. That reading is your body temperature, which gives us an important indicator of your health. Remember, proper technique ensures accurate measurements, which are crucial for proper diagnosis and care. Let's take a closer look at the laboratory thermometer. It consists of a long, narrow glass tube with a bulb at one end that contains mercury. The mercury is crucial because it expands and contracts with temperature changes, allowing us to measure temperature accurately. The scale on the thermometer is marked in degrees Celsius or degrees C, which is the standard unit for measuring temperature in most scientific contexts. Typically, a laboratory thermometer can measure temperatures from about C up to 110 degrees C. This range makes it versatile for many experiments and applications. Overall, the design and features of this thermometer are tailored for precision and reliability in a laboratory setting, helping us monitor and record temperature changes effectively. Let's go through how to measure temperature with a laboratory thermometer. First, take some tap water in a beaker. Now, dip the thermometer into the water, but make sure the bulb of the thermometer does not touch the bottom or the sides of the beaker. This is important because contact with the sides or bottom can give inaccurate readings. Hold the thermometer vertically so it stays steady. As you do this, you'll notice the mercury level begins to rise. Wait patiently until the mercury level becomes steady. That's when the temperature reading is stable. Once it's steady, note the level of the mercury. This reading corresponds to the temperature of the water. Remember, the key is to ensure the thermometer is properly immersed and held upright for an accurate measurement. This process is essential for understanding how to measure temperature precisely in a laboratory setting. Let's talk about the transfer of heat. Essentially, heat always flows from a body at a higher temperature to one at a lower temperature. This natural movement is what we call the transfer of heat. Now, there are 3 main ways this transfer happens. First is conduction, which is basically heat moving through a solid material. Think of how a metal spoon heats up when placed in hot water. The second is convection, which involves the movement of fluids, liquids or gases, where warmer parts rise and cooler parts sink, like in boiling water or atmospheric weather patterns. Lastly, radiation is the transfer of heat through electromagnetic waves, which means it can occur even through empty space, like the heat from the sun reaching Earth. Understanding these methods is crucial because they form the foundation for many applications we encounter daily, from designing energy-efficient buildings to understanding weather systems. All these processes are interconnected and vital to how heat moves around us in the physical world. Let's talk about conduction. Conduction is the process by which heat is transferred through solids, moving from the hotter part of the object to the colder part. It's a fundamental way heat moves in materials like metals and other solids. Now, to understand this better, I have a simple activity for you. Take an iron or aluminum rod and fix a few pieces of wax at equal distances along its length. Clamp the rod securely to a stand and then heat one end of it. What you'll observe is that the wax pieces start to melt one after the other, beginning from the heated end and moving toward the cooler end. This melting shows us that heat is being transferred along the rod through conduction. The heat travels from the hot end to the cold end, causing the wax to melt as it reaches each point. This activity helps us see that conduction is all about heat moving through a solid material, without the material itself moving. It's an important concept because it explains how heat spreads in many everyday objects and materials. Understanding conduction is key to grasping how thermal energy moves within solids, which ties into the overall theme of heat transfer methods. Let's talk about conductors. Conductors are materials that allow heat to pass through them easily. Think of them as the highways for heat energy. When heat comes into contact with these materials, it flows through quickly and efficiently. Some common examples of conductors include iron, aluminum, and copper. These materials are widely used in everyday objects, like cooking pots and electrical wiring, because of their ability to transfer heat or electricity effectively. Understanding conductors helps us see how heat moves in different materials, which is an important part of the overall theme of thermal and electrical energy transfer. Now, let's talk about insulators. Insulators are materials that do not allow heat to pass through them easily. This means they help keep heat contained, whether you're trying to keep something warm or cool. Some common examples of insulators include wood, plastic, glass, rubber, air, and water. You'll notice these materials are often used in everyday items like handles on pots, double-glazed windows, and insulation in walls. Understanding insulators is important because they play a crucial role in controlling heat transfer, which ties back to our overall theme of how materials interact with heat and electricity. By using insulators wisely, we can improve energy efficiency and safety in many applications. Let's talk about convection. Convection is a process where heat is transferred through liquids and gases. Basically, it happens when the hotter parts of these fluids move toward the colder parts, carrying heat with them. This movement creates a transfer of energy that is really important in many natural and industrial processes. For example, think about boiling water or the way the atmosphere circulates. The key point here is that convection relies on the movement of the fluid itself to transfer heat, unlike conduction, which involves direct contact. Understanding convection helps us see how heat moves in our environment and in technology, tying into the bigger picture of heat transfer mechanisms. Now, let's look at an interesting activity that demonstrates how heat transfer by convection works in practice. Take some water in a round bottom flask and place it on a tripod stand. Next, add a crystal of potassium permanganate into the water. Then, carefully heat the water with a burner. As the water at the bottom gets heated, it becomes less dense and rises upwards. Meanwhile, the cooler, denser water from the top moves downward to replace it. This continuous movement creates a convection current. What's important here is that this process shows how heat is transferred through the movement of fluids, in this case, water. And this activity clearly illustrates the key concept of convection, where hot fluids rise and cold fluids sink, transferring heat throughout the liquid. This is a fundamental way heat moves in many natural and industrial processes, linking directly to our overall theme of heat transfer methods. So let's talk about convection in air. When a heat source, like a flame, is present, the air right above it gets heated up. As it warms, it becomes less dense and naturally rises upward. This creates a cycle where cooler air from the sides moves in to replace the rising hot air, then heats up and rises themselves. This continuous movement is what we call convection. Now, to make this clearer, imagine placing one hand above a flame and another on the side. The hand above the flame feels the heat more intensely because of the hot air rising directly from the source. The hand on the side, however, doesn't feel as hot because it's not in the direct path of the rising hot air. This demonstrates how convection causes heat to be transferred through the movement of air, which is a key concept in understanding how heat spreads in our environment. Connecting this to the overall theme, convection is an essential process in many natural and everyday situations, from weather patterns to heating our homes. Understanding this cycle helps us see how heat is transferred efficiently through the movement of air. All right, now let's talk about the sea breeze. During the day, the land heats up much faster than the sea does. This causes the air above the land to become hotter and to rise. As the warm air rises, cooler air from over the sea moves in to replace it. This movement of air from the sea toward the land is what we call a sea breeze. It's a great example of how temperature differences influence local wind patterns, which ties into the bigger picture of how our atmosphere works. So essentially, the heat differential between land and sea during the day drives this refreshing breeze from the ocean inland. Now let's talk about the land breeze. During the night, the sea cools down more slowly than the land does. This difference in cooling causes some interesting air movements. The hot air that was rising over the sea during the day starts to cool and sink, but since the land cools faster, cool air from the land begins to move toward the sea. We call this movement a land breeze. It's a natural process that helps balance the temperature differences between the land and the sea and plays a key role in local weather patterns. Understanding this movement is important because it connects to the overall theme of how natural forces work together to create our climate and weather systems. Now, let's talk about radiation. Radiation is a fascinating way heat moves from one place to another without needing any medium like air or water to carry it. For example, think about the heat from the sun. It's reaching us through radiation. When we sit near a fire, we can feel the warmth, and that's because the fire radiates heat directly to us. The key point here is that all hot bodies radiate heat, sending it out in the form of electromagnetic waves. This process is especially important in understanding how heat transfers in environments where no medium is present, or when the medium doesn't conduct heat well. So, in the big picture of heat transfer mechanisms, radiation plays a crucial role in many natural and technological processes. Now, let's look at how different surfaces absorb heat through two simple tests. First, the absorption test. Imagine taking two tin cans of the same size, paint one black and the other white. We pour the same amount of water into each and leave them in the sunlight for about an hour. What do you think happens? The water in the black can will become warmer than in the white can. This shows us that dark surfaces, like black, absorb more heat from sunlight, increasing their temperature more quickly. Next, we have the radiation test. Again, take two cans of the same size, paint one black and the other white. But this time, pour hot water, say at 60 degrees Celsius, into each and leave them in a shaded room or in the shade for about 10 to 15 minutes. What do you notice? Interestingly, this time, the water in the black can will be cooler than in the white can. This tells us that black surfaces also emit radiation more effectively, losing heat faster in certain conditions. Connecting these ideas, we see that surface color affects heat absorption and radiation differently depending on the environment. In sunlight, darker surfaces absorb more heat, leading to higher temperatures. But in shaded conditions, or when radiating heat away, the same dark surfaces can lose heat more quickly. These concepts are vital for understanding how surfaces interact with heat, which ties back to our overall theme of heat transfer and energy efficiency. Let's talk about clothing choices in different seasons. In winter, we tend to wear dark-colored clothes. The reason for this is that dark colors absorb more heat from the sun, which helps keep us warmer in cold weather. Conversely, in summer, we prefer light-colored clothes because they reflect most of the heat, helping us stay cool under the hot sun. Now, an interesting fact is about woolen clothes in winter. Wool is a poor conductor of heat, meaning it doesn't let heat pass through easily. Plus, the air trapped between the wool fibers acts as an insulator, preventing heat from escaping our bodies. This combination makes woolen clothes very effective at keeping us warm during cold months. So overall, our clothing choices are closely linked to how our clothes interact with heat, either absorbing it to stay warm or reflecting it to stay cool. And this ties back to understanding how heat transfer affects our daily lives.